My goal is to solve this logarithmic equation. I'm going to notice I have logarithms on one side of the equation and a constant on the other side. When I have an equation that has this general form, what I'm going to go for is to use the fact that I can use log base something of some expression equals a constant and rewrite it in its exponential form, which is base to the power, my exponent's on the other side of the equal sign, equals my expression. That's what I'm going for here. Now I'm going to notice on the left, I don't quite have that form yet. I have two separate logarithmic expressions. They do have the same base, though. That's good. That means I can use a property of logarithms to rewrite them as a single logarithmic expression. So I'm going to write log base 6 of, let's see, my logarithms are added. That means I can write as a single logarithm with my two expressions multiplied. So I have x plus 3 times x plus 4 equals 1. And now I do have exactly the form that I need. Log base 6 of some expression equals a constant. Here we go. My base is 6. Exponent is over here to the first power equals the thing I was trying to take the log of. So I'm going to go ahead and multiply this out. I have x squared, and then I have plus 3x plus 4x is 7x, and then 3 times 4 is 12. So now I have a quadratic equation. Well, we have some tools for solving quadratic equations. The main two are factoring and the quadratic formula. For both of those, the next thing that I need to do is get all of my terms on one side, 0 on the other. So I'm going to subtract 6. So I have a 0 on the left. Now I have x squared plus 7x plus 6. The quadratic formula does work all the time, so if you're comfortable with that, you can certainly use that. This will factor, and factoring tends to go a little quicker, so I'm going to factor. I have 0 equals, and two numbers that multiply to positive 6 and add to positive 7. 6 times 1 is 6, and 6 plus 1 is 7. So x plus 6 times x plus 1 will do the trick. Now I'm going to take each of my factors and set equal to 0 individually. X plus 6 equals 0. I'll subtract 6 on both sides to get x equals negative 6. X plus 1 equals 0. Subtract 1. X equals negative 1. But I'm not going to get excited just yet. Our equation had logarithms in it. The domain of a logarithmic function is positive values only, so I have to check and make sure I'm not trying to take the logarithm of anything that's outside its domain of anything that's negative. Sometimes when we check, we kind of say, oh, if you want to check, you can. See if you got it right. But this is not one of those times. This is we have to check because we might have an extraneous solution that looks like a solution but really isn't. So I'm going to take negative 6 and 1 at a time, and check in my original equation before I did anything at all to change it. Here we go. I have log base 6 of negative 6 plus 3. And at this point you should hear squealing tires and needles scraping across vinyl records because negative 6 plus 3 is negative 3, which is outside the domain of a logarithmic function. I can't do that. Log base 6 of negative 3, not going to happen. So negative 6 looked like a solution, but it's not. It's extraneous. It will not work in the original equation, so we have to throw that one out. Well, we have one remaining hope for a solution to this equation, so let's try it. Let's try x equals negative 1. Starting at the beginning again, log base 6 of negative 1 plus 3. Well, negative 1 plus 3 is positive 2. That's good. I can do log base 6 of negative 2, so I'm going to keep going. Plus log base 6 of negative 1 plus 4. Well, negative 1 plus 4 is positive 3. I can take a logarithm of a positive value. Equals 1. There's nothing to do over there. Hey, look at that. We tried it. We get something that's doable, usable. So x equals negative 1 is, in fact, a solution to this equation. It's the only solution to this equation, and we'll keep it.